Hi everyone, my name is Rajul Sakivar and I am pursuing a master's degree in IT innovation at the University of Nebraska, Omaha. Today I am excited to present you an in-depth exploration of the clique problem. So this topic brings together ideas from graph theory, computer science and optimization methods. So in this next few minutes, we'll look at why the clique problem is important, the challenges it presents, and how it's used in real world situations, and also the advanced techniques like metaheuristics and quantum algorithms that researchers are using to solve it. So we will cover the following topics in the upcoming slide. So we'll start with introducing the clique problem, explaining what techniques are and the different challenges they present. We'll then explore why the clique problem is NP-complete, including a proof to show that it it is complex and why solving it efficiently is difficult. I'll share some real world applications, such as how the problem is used in social networks and biology. We'll also discuss metaheuristics approximate methods for solving large instances, and I'll also touch on how quantum computing might help with NP complete problems in the future. So by the end, we will have the better understanding about the importance and the complexity of the clique problem across various fields. So finally, I'll wrap up with some key takeaways and the references. So introduction to clique problem. So let's start with the basics. So what is a clique? So its definition is a clique in a graph G is a subset C where every pair of distinct vertices are connected. In these figures, a clique is a subset of these dots where each pair is directly connected. So we can see in both the graphs. So for example, the nodes 1, 2 and 3 are connected to each other. So this is a clique of size 3. In the next graph, we can see the nodes 1, 2, 3, 4 are connected to each other. So this is a clique of size 3. So in real world, for example, we can think of a group of friends where everyone knows each other. So that is a clique. So the goal in the clique problem is to find the largest such group within a given network. So there can be two versions of the problem. So first is decision version. So given a number k, so can we find a clique of size k? And second is optimization version. So what is the largest clique we can find in the entire graph? So this might sound simple, but as we'll see, it's very challenging problem, especially for the large networks. NP completeness of the clique problem. So why is the clique problem is NP complete? So to prove that a problem is NP complete, we have to show that it belongs to both NP and NP hard classes. Because NP complete problem is NP hard problems, which also belongs to NP. So now first we will prove that the clique problem is NP. So to show that the clique problem is NP, we need to explain how we can check if a solution is correct quickly in polynomial time. So if we are given a set of k vertices that are supposed to form a clique, we can verify this by checking if each vertex is connected to every other vertex in the set. In a clique, every pair of vertices must have an edge between them. So for each of the k vertices, we can check if it is connected to other k minus 1 vertices. This means we have to check all the pairs of vertices in the end, and the total number of pairs is k into k minus 1 by 2, which is around order of k square time. So as we can see here in the graph, I have given an example. So let us take a clique of size 3 consisting of nodes 1, 2 and 3. So how many times we need to check for each node? So for example, node 1 we have to check for node 2 and 3 if node 1 is connected to them. So for every node we have to check k minus 1 by time. So for all the nodes k, the total time taken would be k into k minus 1 by k into k minus 1. So why we are dividing by 2 is every time we are counting a vertex twice, because when we are checking for the node 1 we are counting 2 and the edge between 1 and 2. So while we will count again, the edge between 2 and 1 will again include the edge between 1 and 2. So we are counting each edge twice, so we are dividing here by 2. So the time to check if the solution is correct is proportional to order of k square, which is a polynomial time. So this means the clique problem is NP because we can verify the solution quickly in polynomial time if we are given it. So now is NP-Completeness of the clique problem. So now I'm showing how the Boolean satisfiability problem, which is 3 set, reduces to the clique decision problem, which helps us to prove that the clique problem is NP hard. So to prove that the statement the clique problem is NP hard, we need to show that set problem reduces to the clique decision problem. So let us take a Boolean expression f, which is a function of x1, x2, x3. So the function is x1 or x2 and x1 complement or x2 complement and x1 or x3. So where x1, x2, x3 are variables, double end is logical end and double OR is logical OR. Now in graph construction, to represent this Boolean expression as a graph, we need to create vertices and edges. So each vertex represents a literal and the clause it belongs to. So for example, x1 comma 1 represent variable x1 in clause 1 and x1 complement 2 represent the complement of x1 in clause 2. So overall we have 3 clauses, C1, C2 and C3. So we have some rules which are applied while creating the edges in the graph. So first rule is no edges exist between the vertices in the same clause. So for example, we have a x1 comma 1 and x2 comma 1. They cannot be connected because x1 also belongs to clause 1 and x2 also belongs to clause 1. Second condition is no edges exist between a variable and its complement. For example, x1 comma 1 and x1 complement comma 2 cannot be connected because they are complement to each other. I'll take an example of a subgraph. So for the Boolean expression, consider the subgraph formed by vertices x1 complement 2, x2 1 and x3 3. You can also see in the figure that these 3 nodes are connected by dotted lines. So these vertices form a clique of size 3 because they are connected to each other. Now when we substitute the value of x1, x2, x3 as 0, 1, 1, the expression evaluates as follows. So 0 OR will be 1, 1 OR will be 1 and 0 OR will be 1. So if we perform AND operation for all the 3 ones, then we'll get the final output as 1. So what is the conclusion here? So if we can find a clique of size k where k is the number of clauses in the boolean expression, then the expression is satisfiable. Second, this reduction shows that the clique problem is NP-hard, because if we can solve the clique problem, we can also solve the three set problem, which is NP-complete. Now some real world applications. So the clique problem is not just theoretical, it has many real world applications. So first is social networking. On platforms like Facebook or LinkedIn, the algorithms looks for group of people who are who are all connected to each other. These groups are called cliques. By understanding these groups, the platform can suggest new friends or identify important group of people like influencers or communities, which helps improve the overall user experience. In biology, especially when studying protein inside cells, a clique can represent a group of protein that works together. By finding these groups, scientists can better understanding how the protein interact to carry out the important task, which is the key to understand how cells function and even how disease develop. So third example of the clique problem is computer networks. So in computer networks, finding the largest clique, so basically a group of interconnected devices, can help optimize how resources like bandwidth or processing power are used. It can also identify which connections are the most critical for the network to function properly, ensuring stable and efficient communication. So these applications show how solving the clique problem can be significant, can have a significant impact on various fields. Now we'll discuss the meta-heuristic and approximation algorithms. So why meta-heuristics? Since solving the clique problem exactly is computationally expensive, we often use meta-heuristic algorithms to find approximate solutions. These are strategies that guide other algorithms to search for good solution efficiently. So the first example is simulated annealing. So this method is like how metal is heated and then cooled slowly to remove flaws. So in the algorithm, we start with a random solution and make small changes to it. Sometimes we allow the solution to get worse for a moment to help the algorithm escape stuck situations called local minima. This helps the algorithm explore more possibilities and over time settle in a better situation. So second example is ant colony optimization. So imagine ants finding the quickest way to food. They leave a scent trail that other ants follow. In ACO, the algorithm uses artificial ants that explore different solutions. When ants find a good solution, they leave a scent called the pheromone to mark the path. Other ants are more likely to follow stronger paths. So over time, the algorithm focuses on the best solution as more ants follows the best paths. So this method helps find good solution to tough problems like the clique problem. So among these, simulated annealing is widely used for the clique problem because It balances exploration and exploitation well, providing good quality solutions without excessive computation. Now we'll discuss the quantum algorithms for the clique problem. So quantum computing is an exciting new frontier that could potentially solve NP-complete problems like the clique problem much faster than the classic computers. So the quantum approximate optimization algorithm is an example which encodes the graph into quantum states and optimizes a cost function. So it's designed to handle combinatorial optimizations problems, including finding the largest clique. So how does this work? So it works by turning the problem into a quantum state using two main parts. One that represents the problem's goal, the cost function, and other that helps explore different solutions. So this algorithm apply quantum operation to gradually improve the solutions. It combines both quantum and classical computing, where quantum steps helps evolve the solution and classical optimization adjust the settings. While this algorithm gives approximate solutions, it can handle tough problems more efficiently than the traditional methods. Yeah, but while these methods are still in the early stages of the development, they represent a promising direction for the future research and may eventually offer breakthrough in solving NP-complete problems more efficiently. So here are some references I have provided. So these are some two papers which are which have explained the quantum approximate optimization algorithms. Now we are on the conclusion slide. So in summary, the clique problem is a fundamental NP-complete problem. This means that finding the largest clique in a graph is inherently difficult and no known algorithm can solve it quickly for the large graph in the worst case. So it belongs to a category of problems for which solutions, if they exist, are hard to find and take a lot of time, especially as the graph grows in size. So second conclusion is meta-heuristic like simulated annealing and ant colony optimization offer practical solutions. So while finding an exact solution to the clique problem may be challenging, methods like simulated annealing and ant colony optimization provide approximate solutions. So these approaches are not guaranteed to always find the best solutions, but they offer give good enough answers within a reasonable amount of time, making them useful for real world problems where exact solutions are not always necessary. So our third takeaway is quantum computing holds future for potential for solving it faster. So quantum computing is an emerging field that has the potential to solve certain types of problems much faster than classical computers. So for the clique problem, quantum algorithms like quantum approximate optimization algorithms, which we discussed in the previous slides, could potentially provide solutions more efficiently. While still this is in early stage, quantum computing could significantly change how we approach NP-complete problems in the future. So these are some good references I have gone through. Yeah, thank you for watching the video.